All right, guys, so we got normal as an approximation to binomial. So we're going to use the normal distribution to approximate binomial distributions sometimes. Method for using a normal distribution as an approximation to binomial probability distribution. So that some problems involving proportions, that's what we're going to deal with, proportions or percentages, can be solved by using a normal distribution. Now, watch carefully when you can and when you can't do this. Here's the deal. If the conditions of n times p is greater than 5 and n times q, don't forget what those are. P is probably the success, q is probably the failure. If they're both satisfied, if they're both bigger than 5, then you can use the binomial probability distribution to approximate very well. You can use a normal distribution to approximate a binomial probability. Don't forget our mean is n times p, standard deviation, square root of n times p times q. That's standard for binomial distributions. That'll also work with our normal distribution if this is true. If n times p is bigger than 5, n times q is greater than 5. Both have to be true. Okay, quick review on what exactly binomial is, when you can use this. Binomial has a fixed number of trials. Like you may say there's 100 of something being done. Each trial is independent. One trial does not affect the next one. One outcome does not affect the next one. Each trial must have outcomes classified in 2 categories, success and failure, boy, girl, blue, brown, whatever. The probability of success remains the same in every single trial. It doesn't change because they are independent. Okay, approximation is a quick summary slide here. N times p must be greater than 5. N times q must be greater than or equal to 5. If that's the case, that's how we're going to find our mean. That's how we're going to find our standard deviation. And it has a normal distribution. And you know what that looks like. Okay, 6 steps. Sorry about that. 6 steps you must take. Number 1, if you're going to try to do this. Number 1, verify that both of these are bigger than 5. You can use your calculator, whatever. Do that. If they're not, then you're done already, and you must do the regular binomial stuff that we've already learned how to do. After you verify that that is true, find your mean and standard deviation using those formulas. Identify your x, your discrete whole number x that the binomial problem is talking about, and we're going to focus on that value temporarily because we're going to change it just a little bit. Number 4, that's where it gets a little crazy. Draw a normal distribution centered around the mean. That's what a normal distribution do. With a vertical strip area centered over x. Mark the left side of the strip with the number x minus 0.5 and the right side equal to x plus 0.5. Consider the entire area of the strip to represent the probability of discrete whole number itself. So we're going to take the whole area there from negative 0.5 below it to positive 0.5 above it and consider that to be basically just our x. Number 5, determine whether the x value of x itself is included in the probability. Determine whether you want the probability of at least x, at most, more than, fewer than, or exactly x. Shade the area to the right or left. Also shade the interior strip if and only if x itself is to be included. This total shaded region corresponds to the probability being solved. So a little bit different. Okay, here's the procedure for normal distribution. Use x minus 0.5, x plus 0.5 in the place of x. We're not going to use just flat out x. Find the shaded region, find the z-score, use that z-score to find the area to the left, blah, blah, blah. Use the cumulative area on your calculator or StatCrunch. Let me show you an example. Best way to do it. In 431 NFL football games that went to overtime, the teams that won the coin toss went on to win 235 of those games. What they do is they toss a coin before each of the overtimes to see who gets the ball first. If the coin toss method is fair, teams winning the toss would win about 50% of the games. We'd expect 215.5 instead of the 235, which we're trying to figure out why that happened. Assuming there's a 0.5 probability of winning a game, that means there's also a 0.5 probability of losing the game. Find probably going to get at least, that's the key word, at least 235 winning games, which is what this is right here. Okay, first thing, check n times p and n times q. Well, n is 431, p is 0.5, which also means q is 0.5. Multiplied it out, got 215 both times, which is both bigger than 5, so step 1 is good. Step two is find the mean and standard deviation, so I did n times p, found that, that's our mean, which we already knew. Standard deviation, 10.38. Now, what I need is a probability of at least 235, so remember the vertical strip. When I draw my picture in just a second, you're going to see this. Let's say 235 is about right here. Well, first of all, the mean was 215, so the mean is 215.5. 235 is here, but remember, we have to go, that's 235. We got to go 0.5 less than that. That's 234.5, and 0.5 more than that, 235.5. And I want at least that, so I'm actually going to be shading everything past there. And I'm going to show you the next slide. It's a little prettier. Here's our pictures, right, of 234.5. Now, because it says at least 235, it actually includes the 235, which means I'm going to start shading at the first strip, the 234.5, and shade everything to the right. Found my z-score. Of course, with StatCrunch, you don't necessarily have to use a z-score. You can use your mean and your x. Well, actually, your x is 234.5, and just do greater than your x. What happens is you find out, there's your z-score if you want that. And once you do the z-score or just punch it in StatCrunch, you're going to find out the probability is 0.0336 that for the coin flip winning team to win at least 235 games. And that's a very low probability or proportion. And because it's so low, it's below 0.05. That means it's statistically significant, don't forget, which means that means the team winning a coin flip does have an unfair advantage because so many teams win after winning that coin flip. So not really a fair way of doing overtime. When we use a normal distribution, which is continuous, as an approximation for the binomial, which is discrete, a continuity correction. That's why we do the negative 0.5 and positive 0.5 to make the fact that we're doing a continuous distribution to solve a discrete problem. And the next slide has a summary of what to do when. This is a very important slide. It's the last slide on the video. I'll take a picture, I would do something of it. The notes are important off this slide. Okay, so if you see the word at least, and I'm using a 235 because that's what we use in our example. So 235 is using all these. If it says at least 235, remember we do our little surround. We're going to go from 234.5 to the right, 234.5 to the right. If it says more than 235, that doesn't include 235, so we start at 235.5 and shade to the right. If it says at most 235, that includes everything from 235 and below, which means you start at 235.5. You start past it and include it. If it says fewer than 235, it does not include 235, so you start at 234.5 and shade to the left. And if it says exactly 235, like exactly, we're going to go between 234.5 and 235.5, that little area right there, because we can't do exactly 235 because we're using a continuous distribution to do a discrete problem. So hope that made some sense to you. We'll work on it in class like we always do. But I would get this last slide especially, just see if you can figure out the 0.5 situation, because once you do that, the rest of it's just normal distribution like we've been doing. I'll see you tomorrow.